Welcome to chapter 10, everyone. This chapter, we are going to be talking about parametric equations and polar equations. This is one of the few chapters that you actually need for third semester calculus. Much of the stuff that you learn in second semester calculus, you don't need as much in third semester. But parametric and polar equations definitely are among them. Let's start with parametric equations, and we're just going to talk about them a little bit. No calculus for this lesson. So imagine that a particle is traveling along a curve C. So here we have a particle moving through maybe a magnetic field or something like that. And what we can do is they have an X and Y coordinate, but there's a third factor. There's a time factor. Now, T doesn't always stand for time, but there's a parameter of some sort that affects. So you can imagine after 2 seconds, the position X comma Y that's here. And after 5 seconds, the position is X comma Y here, as we're looking at that. So both X and Y independently depend on the parameter, in this case, T. Sometimes the parameter is T, sometimes it can be theta, it can be whatever you need it to be. And in third semester calculus, you'll have more than one parameter. All right, so for example one, we're going to sketch and identify the curve defined by the parametric equations. And so here's our first set of parametric equations. X equals t squared minus 2t, and y equals t plus 1. Now, what I did was I set up a table here to save us a little bit of time. When t equals -2, and I plug -2 into here and here, I'm going to get 8. And when I plug -2 there, I get -1. And so you can see at time equals -2, we're way back here. And then as time is progressing, notice we're going in this direction. Now I want to talk about that for a minute. This direction is considered counterclockwise, or this one is considered clockwise. A positive orientation is counterclockwise, but you can see it didn't come out all that great, but there are arrows on this indicating what direction this is going. So with parametric equations, we not only get the curve, but we get the direction that the curve is moving. Now I want to point out, if I wanted to, I'm hoping you can see that this is a sideways parabola. And so what I'm going to do is I'm going to take the equation y equals t plus 1 and rewrite it as t equals y minus 1. And now I'm going to plug it into here and here. And then we'll be able to see our function. So x is now a function of t. It was a function of t, it's now a function of y, pardon me. And that's going to give us y minus 1 squared minus 2 times y minus 1. And let's clean that up a little bit. So x is going to equal y squared minus 2y plus 1 minus 2y plus 2. And here is this curve, a sideways parabola. So we can go back and forth between them as we do that. You could see if I was given this, I would be able to replace t with the y minus 1 and then come up with it. So we can go backwards as well. All right. Moving on, general curve is represented with parametric equations, and you'll see me write it sometimes instead of x equals a function of t, I'll write it x of t and y of t. So sometimes you use f and g, sometimes you use the same x and y. In general, the curve represented with parametric equations, x is a function of t and y is a function of t, where t goes from a to b, has an initial point when t equals a, this is when t equals a, and a terminal point of when t equals b. So we're going to take a look at another example. What curve is represented by x equals cosine t and y equals sine t, where t goes from 0 to 2 pi? Well, let's set up a txy table. And we'll start when t equals 0. T is pi over 2. T is pi. 3 pi over 2. And 2 pi. And as we plug t into here and here, you can see we end up with cosine of 0 is 1, sine of 0 is 0. And Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Cosine of pi is -1. Sine of pi is 0. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is -1. And 2 pi is the same as 0. And I'm hoping we can see a pattern here. And if we go to 1, 1, -1, -1, I'm hoping that we can see that we have a circle. And when t equals 0, we're starting up here. I'm sorry, we're starting here. And then when t equals pi over 2, we're going to 0, 1. So we're actually going that way. And remember, I mentioned counterclockwise is considered a positive orientation. So let's eliminate the parameter again, kind of like what we did up here with the parabola. And what I'm going to do is I'm going to write cosine squared of t plus sine squared of t is equal to 1. We know this. However, cosine squared t is actually x squared. Sine squared t is y squared. And that still is going to equal 1. This is the unit circle. Kind of cool stuff. Let's move on to the next page. All right, what curve is represented by x equals sine of 2t and y equals cosine of 2t, or 0 to 2 pi? Now, what we're going to get is, and let's just real quick eliminate the parameter again. Sine squared of 2t plus cosine squared of 2t equals 1. So this is now x squared plus y squared equals 1 again. So it's going to be the unit circle, but it's a little bit different. Because of the 2, we're actually going to go all the way around, and we're going in a clockwise position. Let me show you how I know that. And I'm going to show you how kind of useless this particular method is. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the reason this is not going to work is because when I plug in 0 here, I get 0. Plug in 0 here, cosine of 0 is 1. Now, when I plug in pi over 2 here, do you see that that's going to give me sine? The 2's will cancel, and that's just going to be sine of pi. That's 0 again. And when I plug in pi over 2 there, that's going to give me pi, and that's going to give me a -1. In fact, all of these, when I plug them in for the x coordinate, are giving me zeros. And for this one, it just alternates. So that's going to give us, once again, a unit circle, but because t is going from 0 to 2 pi, it's actually going around the unit circle twice. And in the wrong direction. And we can see we're starting here, 0, 1, and now we're going in a clockwise direction as t is increasing. And it's going around twice on this interval. However, we're going to come up with yet another unit circle. So once again, sine squared of 1/2 t plus cosine squared of 1/2 t. It's going to equal 1. Again, this is x squared plus y squared equals 1. So once again, we have the unit circle. However, because of the 1/2, and because we're going from negative pi, so this would be t, x, and y. And notice our interval is different. So this starts at negative pi. Then we'll go up to negative pi over 2, 0, pi over 2, then pi. And as we plug this in, negative pi into here and here, we're going to end up with negative 1, 0. When we plug this in, we're going to get negative pi over 4. This is going to be negative root 2 over 2. This will be positive root 2 over 2. Plug in 0, we get 0, 1. Plug in pi over 2. We're going to get, again, that's going to be pi over 4, so that's root 2 over 2. And when we plug in pi, it's going to give us a 1 and a 0. Now you'll note this is only going to go across 2 quadrants. In fact, it's only going to be the top half in this case. So at negative pi, we start here. And then we're going to end up here at negative root 2 over 2, positive root 2 over 2. And then end up here. So this one, once again, is going in the clockwise direction. But it's the only the top half. Again, that's because of the 1/2. Even though we went a full 2 pi distance from negative pi to pi, but it's just half of the circle. All right. Next up, we're going to eliminate the parameter and sketch the curve as t goes from 0 to pi over 2. So for this one, I'm going to set up the t, x, and y. And remember, cosecant is the reciprocal of sine. So whatever we get for x, the reciprocal is going to be for y. And I'm going to break this up like this, just so we get an idea of what we're doing. Pi over 6, pi over 4, pi over 3, up to pi over 2. So when we plug in t equals 0, we get a 0 for sine, and this is undefined. So x can't be 0. T can't be 0 in this case, because it makes x equal 0, and the reciprocal of that, we have a problem with y there. At pi over 6, we get 1/2. Sine of pi over 6 is 1/2, and the reciprocal of that is 2. Pi over 4, it's root 2 over 2. Reciprocal of that is just root 2. Remember, originally root 2 over 2 was 1 over root 2. This is root 3 over 2, making the reciprocal 2 root 3 over 3, and 1 and 1. Now let's eliminate the parameters so we get an idea of what it is that we're doing. I notice if I take x times y, that's sine t times cosecant of t. Remember, they're reciprocals, so this is just xy equals 1. And this becomes y equals 1 over x. So we know that x can't be 0, right? We have a problem. We'll be dividing by 0 there. So we kind of have an idea of what this is supposed to look like, but this is only going to be part of the graph. And if you remember this, it's asymptotic on the x and the y axis. And you can see right here, if x equals y, or if x equals 0, pardon me, then 0 equals 1. That's an inconsistency. Same with plugging in a 0 for y. So what we're going to end up with is the point. This is the final point is going to be at 1, 1. Is going to be right here. And this is going to look like this, and it's going to stop right there. And we can see as t is increasing, we are this is the end point. So we tried to start at 0, it's asymptotic here. Oops, I did. And so as t is increasing, we're going this way until it ends here. So this is the terminal point. All right. So now we're kind of getting a feel for what parametric equations are doing for us. We'll talk about one more, and then we have a really cool one at the end here. All right. So sketch the graph, and we've already done that. And what we're going to end up with in this case is, because x is sine t, what we end up with when I replace sine of t with x, we get y equals x squared. And you can see our parabola. And here's what's happening. This is just going to be bouncing back and forth because we know that sine is only going to go between -1 and 1. So that means x is only going to be between -1 and 1. Y, however, is going to be positive because we're squaring it, and it's going to be everywhere in between. So this is literally bouncing back and forth as t is increasing as high as we want it to go. So yeah, it's like it's just bouncing around there. All right, now we are to the cool stuff. That's the cycloid. And I want to define the cycloid for you. And I think the easiest way to do that is for me to show you something I found in Wikipedia. This is showing how a cycloid is made. So you get a point that is on a circle and it rolls around like that. And you can see it's drawing this shape. It's really cool. Literally, if you type in cycloid and you click on the Wikipedia, this graph comes up. It's pretty cool stuff. So let's switch back. So we kind of have an idea of what we're looking at here with a cycloid, but I want to come up with equations for the cycloid, parametric equations, so that we can do that. And I want to start here. I'm going to start with OT. That's this length here. So from here to here is OT. And can you see if this circle rolls this way, it's going to be the same as this arc right here, meaning OT is the same as arc PT. And because we know a little geometry, we know that arc PT is going to be r theta. Theta, of course, is in radians. Now the center of the circle is at the point r theta, meaning that's the x coordinate of that here. That's this distance here. So that's OT, which we now know is r theta. And this here from C to T, that is a radius. So the center is at r theta for the x coordinate and r for the y coordinate. All right, next up. So we're going to let P just be a generic point, x comma y. That's on the cycloid. Again, this is the cycloid here. So this is like the beginning here. All right. So next up. So we're going to find x. And before I do that, I want to draw a triangle. And our theta is here. So this is this triangle right here. You can see it here. Theta is there. This is P. This is Q. This is R. So you can see, and this is C here, our center. And again, this is our point P. So we can see that the sine, push that up a little. the sine of theta is going to be PQ over R, which means PQ equals R sine theta. In addition, you can do the same thing with cosine. Cosine of theta is CQ over R, which means CQ is R cosine theta. We'll come back to that. All right. So next up, our x coordinate. So that's the x coordinate for the point P right here. Is this distance down here? It's just a short little distance here. From there to there, that's x. X is going to be OT, which we defined up here. So OT minus PQ. Right, here's PQ. So PQ is from here to here. So OT minus PQ is going to give me my x. And we know that OT is R theta. And PQ, we just defined down here, is R sine theta. So we can now say that x is R times theta minus sine theta. So there's our x parameter, where theta is our parameter. Let's talk y now. Y, that's this full distance here, is going to be CT. That's CT, that's this whole length here, minus CQ, which we defined down here, our cosine theta. So CT becomes CT is the R, right? That the whole thing right there, that all of this is R, right? R minus CQ, which we have down here, our cosine theta. So we have that y is R 1 minus cosine theta. So let's rewrite it. X of theta is R theta minus sine theta. And y of theta is R 1 minus cosine theta. So here are our parametric equations for a cycloid. That is super cool stuff. I want to add that theta is going to be any real number. Neat stuff. We'll do more with cycloid in other videos.